I've been doing it. Exactly. Well, example, it's not working through the graphic right now.
You feeling better, Natasha? Okay, we'll get started. You guys have this revised schedule, and actually there's not a whole lot that's revised about it, but I think the two changes I made probably will be welcome changes. You know, for the first test, we had at the time of the test, we had both the take-home quiz and the homework due. All right. So what I've changed here is then, if you look down at the bottom of the first page, this next take-home quiz is actually not going to be due until the Friday that's after the spring break. Okay. But I will still have the homework due at the time of the test. And then also for the next take-home quiz after that for test 3, that again the homework will be due at the test, but the take-home quiz will be due the Friday afterwards to break that up a little bit. Okay. However, unfortunately, with the way it's turned out, I can't do that for the last take-home quiz because we run out of days. Okay, so that is, unless, well, just thinking to myself, one thing I could do is just have it due on the very last day. Actually, we have a single day, a Monday, May the 5th, that's our last class, and I might just make it due then, but we'll worry about that later. Okay. I did make up the test that test is a week from Friday, and I did make that up over the weekend. I haven't yet done the kind of like the practice sets or whatever you want to call it, review sets. That I'm hoping to get that to you guys by Friday. All right. Yeah. Keep looking ahead there, Jenna. Yes, it's a week from Friday. All right. So. And then, of course, there is the homework due this Friday that you guys got last time. Right. Okay, so we're on 4.6. We're three main topics here: the directional derivatives, gradient vectors, and this last one that we haven't covered yet, tangent planes to level surfaces. So just as a review here, the directional derivative, we have a unit vector. That's how the book defines it. And we'll say it's A comma B. All right, so the directional derivative, we use just a capital D in the direction of that unit vector is basically the first component of the unit vector times f with respect to x plus the second component of the unit vector times f with respect to y. And then this can, of course, be written as the vector fx, fy dot a comma b with the dot product. All right. And then the thing is, you want to make sure that when you do one of these problems that you are working with a unit vector. You may have to divide it by something in order to make it a unit vector before you proceed with the problem. And then this gradient vector then is defined, let's see, we use the term grad f or del f, and it's defined as it's a vector partial derivative of f with respect to x, partial derivative of f with respect to y. Of course, if it's a three-dimensional, three variables, then it's f with respect to x, f with respect to y, f with respect to z, and it is a vector, right? Okay, and there's a couple things, properties that the gradient vector has. First of all, it's the direction in which we have the largest directional derivative. The direction in which we have the largest or maximal directional derivative. And the other thing about the gradient is that the magnitude of the gradient is actually the biggest directional derivative at a point. So the magnitude of the gradient, is the largest value of the directional derivative. Okay. All right. Now, and we went through some exercises with computing the gradient and computing the magnitude of the largest directional derivative. All right. Now, going on then to tangent planes, this last topic here, first thing I did is as I mentioned, as kind of a shall we say, a reminder that if our surface is z equaling f of xy, where z can be isolated on one side, all right, then the equation of the tangent plane at some point x sub naught, y sub naught, z sub naught is minus z sub naught equals partial derivative with respect to x evaluated at
Did I turn it off? I don't see it.
y naught x naught, and then plus the partial derivative with respect to y evaluated at that x naught, y naught, times y minus y naught. Okay. So, that's if the surface can be defined like that. Now, I've shown you this strange graph of a surface that we could not isolate the z on one side. And so this is the next thing then for these tangent planes. We're going to look at level surfaces. Now, let capital F of x, y, and z equal some constant k. All right, and let that equation be the equation of our surface. Now, this would be the case where we can't just get z on one side. Oops, we can't get just z on one side. Okay. Oops. What? Please share what? can you clarify what you mentioned there? Please share. Because I think I sent you that homework number 5. All right. All right. Now, this is where, notice all these values, combination of x, y, and z, equal a constant. So this is like those level curves that we talked about before where we had these contour maps. So this is called a level surface. Okay. All right. And that's because it equals a constant. Now let's look at a point on the surface. So look at a point, x naught, y naught, z naught. Let's call the surface capital S. And what we're going to do here, again, we're going to cut the surface with a vertical plane, and therefore we're going to get a curve on the surface. So cut the surface with a vertical plane. And get a curve. We'll call it capital C. And so this curve is on the surface, and it's going through the point P. All right. Okay. Now, the curve that we get then, this is a surface in three-dimensional space. So the curve that we get is a three-dimensional curve, and we're going to call it small r of t. And I've got a diagram here in just a second. This is a three-dimensional curve, or what we had called a space curve. And we're going to represent it as small r of t. And we're going to give it the components x, y, and z. We're going to have it parameterized with respect to some parameter t. X of t, y of t, and z of t. Okay. All right. All right. So basically then, our surface, F, so our capital F can now be seen as, okay, capital F of x of t. X is now a function of t, y is a function of t, and z is a function of t. And this equals our constant k. All right. Now, what I'm going to do with this thing then is take the derivative of each side. And this is all leading up to a result that has to do with the gradient. All right. So what we're going to do here is look at the derivative of f with respect to t, and take the derivative, and of course the derivative of k is going to be, a constant is going to be 0. Now let's look at the, say, the tree diagram here. We have our function capital F, and it's a function of 3 variables, x, y, and z, and we parameterized along this curve, so we have x, y, and z are functions of t. All right. So we're going to use the chain rule using this diagram. And so this branch here is delta F, delta X, delta F, delta Y, delta F, delta Z. And these three branches are dx dt, dy dt, and dz dt. All right. So therefore, that df dt now can be replaced by, okay, we go down our first branch from f to t, delta f, delta x times dx dt. Now let's go down to the second branch, delta f, delta y, dy dt, oops, dy dt, and then the third branch, delta f, delta z, dz dt, and that's all equal to 0. Okay. Now, I'm going to then represent this as a dot product. In other words, we have two things multiplying each other and they're being added up, so we can look at this as the following. This vector composed of which is going to be the gradient vector, delta f, delta x, delta f, delta y, delta f, delta z, dot the dx dt, dy dt, dz dt, and that dot product is equal to 0. In other words, we just multiply the components together and add them. All right. Okay. Now, this thing right here, remember that our curve was x of t, y of t, and z of t. This is the derivative of x, derivative of y, derivative of z. So this is the tangent vector. Or it's r prime of t, and it's the tangent vector. All right. So this is what we have. This is the gradient of capital F. So we have the gradient of capital F, our level surface, dot r prime of t is equal to 0. Okay. Okay. Now this is our tangent vector. This is our gradient. What does it mean when the dot product of two vectors is equal to 0? What's the relationship between those two vectors geometrically?
That's how Miss Happy usually does it.
Perpendicular 90 degrees. Right. So the gradient of F is perpendicular to the tangent vector.
There's only 2 people in this class. 4?
Right.
4 people in this class.
Of C.
Yeah, where's everyone else in the call?
So in particular, let's look at a particular point.
Shout at the computer, you'll hear that. Shout at the computer.
X naught, Y naught, and Z naught on the surface F.
Like
Okay.
Oh, it says we're speaking.
So at these points,
like the middle of the screen.
T, we're going to say T is equal to T naught, whatever value that is.
Oh, no, that's end call.
So therefore,
Don't want to do that.
I didn't know it was like you or something.
Yeah.
Some
What?
the gradient of F at that particular point, X naught, Y naught, and Z naught, dot R prime at T naught is equal to 0. And again, we have the gradient, of course, is perpendicular to the tangent vector.
Just start typing.
All I'm doing here is looking at a particular point. This tangent vector, by the way, is in the tangent plane.
Oh.
So let's look at it.
Oh, it's done. Get the sign. Get the sign. That's the sign.
I don't think you can
He's
We
laughing.
cannot see your lesson. Oh no! Oh no! Oh man! Oh, I'm sorry, guys.
It's okay.
I forgot
It's
to
okay.
click on that one button.
Yeah, and then check to see that it was there.
Where are they?
Whoa, Larry. Yeah.
Can we see the website?
The actual one.
Oh. No, it looks like he's got it.
Now, what is going on now? Sorry.
Really?
Yeah, we're good.
Thank you guys for doing what you guys did there. Get it in there.
Capitalize it, gosh darn it.
Nope.
I really truly. We can hear you. We can hear you. Type in like it's fine or something, make him feel good.
Did you say thanks or something?
Oh, now I see. Now I see Jerry for the first time ever. How is that happening?
Okay, how do we turn that off, guys? I don't want
Okay, I got it.
Click video on top. Wait to him.
No, it's okay.
Okay, we're gonna go video. Okay. Wait, no, wait.
Hang in there.
Okay, oh wait, I'm trying.
What did you guys do differently that I can see you now?
Marcus. No, show stage is not.
Hello?
Yeah, what did we do differently? Just tell him we don't know.
This is Fort Lafayette.
Oh
What
my
is this
God.
thing?
Oh my God.
Okay.
Nope, that's not a thing. Face tracking.
He's not getting.
Okay, well that way I know when you guys are goofing off then, unless you keep the camera at the ceiling, which it looks like that's what it's kind of looking at. Okay, well, I'm gonna get back, as I said, the notes are gonna be posted, sorry that you missed those.
No, okay.
Are we okay?
Yeah, we're good.
Yeah, tell him we can see him, and the lesson's good.
I guess we are.
Lesson's good.
Thanks, Jacob. Well, I don't know how to turn that off. Oh, there we go.
Alright. Sorry, folks.
Pause my video.
My bad.
Okay, alright.
I won't blame it on anybody else. All right, are we ready to proceed? Okay, so here's the drawing that I have. It's a surface, it's a level surface, so this is capital F equals some constant. And so this gray shaped area is the surface. We're looking at a specific point on the surface, and we're cutting it with this vertical plane. So we get a curve here that's along the surface We want to look at this particular point P that's on the surface and it's on this curve, and this R prime, that is the tangent vector at that point. And what we've just shown here is, and this tangent vector is in the tangent plane that you can view it as just laying right there on the surface at that point. And what we see here then is that the gradient vector is perpendicular to this plane. So as a result, because we now have a perpendicular vector to a plane,
Pause our video, so it's just.
what does that mean as far as being able to get
Make the screen
equation
smaller again for a second.
of that particular plane?
the?
By now can identify, aha,
No, it's.
gradient of the perpendicular vector, or the normal vector. And does anybody remember the formula involved with a normal vector and the equation of a plane from the last test? Yeah, okay. So Mary's saying that they're the coefficients. So let me just, this is what you're talking about. Recall, if the vector A, B, and C is perpendicular to our plane, then the equation, as you said, the coefficient A times X plus B times Y plus C times Z equaling some number D is the equation of the plane. The coefficients there are directly from our normal vector. The D, we calculate the D by, if we know a single point on the plane, we fill in the X, Y, and Z, and we can calculate D. We all kind of remember this. So we can calculate D from a single point on the plane. Okay, so we're going to have the same thing here then. Our gradient vector then, of course, is gradient vector F is equal to capital Fx, capital Fy, capital Fz. All right? And this is our normal vector. So therefore, whatever value Fx has, capital Fx has, we multiply that by the x variable plus the value of capital Fy, we multiply it by the y variable, plus whatever value capital Fz has, multiply it by z, and this equals some number d. And again, we get d by plugging in x naught, y naught, and z naught. Okay. So let's look at an example here of doing this. All right, example. Find the equation of the tangent plane and here's our surface, x squared over 4 plus y squared plus z squared over 9 equals 3. So this part here is our capital F, X, Y, Z, and this, of course, is our constant. So this is a level surface. And so let's get the gradient, let's get the capital Fx. And so that's going to be 2x over 4, which is x over 2. Oh, I better give a point here. Sorry, back up here. At the point minus 2, 1, minus 3. Okay. So that's our capital Fx. Our capital Fy is just going to be 2 times y. And capital Fz is going to be 2z over 9. 2 ninths z. Okay. Now, plug this in at minus 2, 1, and 3. We're going to get that capital Fx is going to be minus 2 over 2, which is minus 1. Capital Fy is going to be 2 times 1, which is 2. And Fc is going to be what? 2 ninths times minus 3. And that's going to be minus 2/3 when we simplify it. Okay. So therefore we get this. These are our coefficients. So we have -1 times x plus 2 times y minus 2/3 times z equals some number d. And then we plug in -2, 1, and 3 to get small d. So that's going to be -1 times -2 plus 2 times 1 minus 2/3 times 3. And what do we get here? 2 plus 2 minus 2. So we end up getting, is that right? No, that's, wait a minute. Hold it. Oh, -3. -3. So that's a +2. 2, 2, 2. So we get a 6 here. Okay. So our final answer then is -x plus 2y minus 2/3 z equals 6. All right. By the way, let me put here what I usually do, put in little asterisks by things, especially since I've already just now made up the test, putting an asterisk here by this formula for the tangent, equation of the tangent plane to a level surface. Any question, though, about that one part of the example that I did there? Okay. All right. All right. Now, what next thing we're going to look at here, then, we looked at the tangent plane. We do want to look at what's called the normal line. Equation of normal line. Now, let me just say, again, refresh what I'm talking about here. So say we have a plane, all right? So it stretches out to infinity in all those directions. The normal line, we're talking about a normal line here, not a normal vector. So a line here, it's going to be some line that intersects the plane at a right degree, a right angle, and then, of course, keeps going. So we're talking about a line, not a vector, but it hits the plane at a 90-degree angle. Okay, so let me just put that in English. The normal line to the surface S at point P, x naught, y naught, z naught. So say this is point P right there, is the line passing through P, point P, and perpendicular to the tangent plane. So in this case, we're talking about, the plane that we're talking about is the tangent plane. All right, so let's remember something about, okay, we're talking about the equation of a line. So let's remember this about the equation of a line. To get the equation of a line, we need two things. We need the direction vector of the line and a point that it goes through. Two things. So we need direction vector and a point it goes through. It goes through. All right. So in this case, we know what the direction vector is. The direction vector is the gradient vector. So the direction vector equals the gradient vector, okay? And we know the point we're given, the point is x naught, y naught, and z naught, okay? Right. let me just, okay. So let's just look at let's begin refreshing our memory on something here. We actually had three ways we could write the equation of a line. Right now I just want to talk about two of them. There was the parametric equation. All right, and there was the symmetric equation, or symmetric equation. Okay. Now, in this case here, so the parametric equation, say we're going in the direction A, B, and C, and it's through the point x naught, y naught, and z naught, then it's x naught plus a times t, y equal y naught plus b times t, z equals z naught plus c times t. So where the a, b, and c there are from the direction vector. And t goes from negative infinity maybe to positive infinity. The symmetric equations are, when we solve for t, we get this, x minus x naught over a equal y minus y naught over b equals z minus z naught over c. Okay. So let's apply that to this particular case then, where the direction vector is the gradient. So it's equal to capital Fx, capital Fy, capital Fz, all right, at our particular point. So therefore, the parametric equations then, and this is of the normal line, are the following. Then we have x equal x naught plus capital Fx times t, and this is again where we plug in the x naught, y naught, and z naught to get a number. That's at x naught, y naught, and z naught. Y equals, again, y naught plus capital Fy of t. Again, that's at x naught, y naught, z naught. As z equals z naught plus capital Fz of t. And again, that capital Fz is computed at our point. Now, the symmetric equation then of the normal line that's going to be x minus x naught over the value of capital Fx equal y minus y naught over the value of capital Fy equals z minus z naught over the value of capital Fz. All right. All right. Again, I want to put asterisk by those two equations for the normal line. And let me do one example then of that. Example. So I'm just going to utilize the last example that we did. Find the symmetric equations of the normal line in our previous example. Okay. So in our previous example, the point was minus 2, 1, and minus 3, and the direction vector, or the gradient vector, was bracket minus 1, 2, and minus 2/3. So we've done all the hard work, we just have to plug it into the symmetric formula. So this is going to be x, is that going to be x minus 2 or x plus 2 on the top there for the symmetric? Plus 2, change of sign, good. X plus 2, and my direction here is minus over minus 1, equals y minus 1 over my direction of 2 equals, now here it'll be z plus 3 over my direction of minus 2/3. And I'm not concerned with you simplifying that minus 2/3 in the denominator. That's fine. Okay. So asterisk there, something like that. Make sure you know how to do. All right. The last thing in this section, and because of technical problem, I was hoping to make it through the whole section, but then we got waylaid with some technical problems. Let's just look here at the last thing they talk about is just the significance of the gradient vector. So they have a little discussion in the book about this. Okay. Now, as I had mentioned before, the gradient vector gives us the direction of the maximum increase of the function. It gives us the direction of the maximal directional derivative. So given a function f, x, y, z, where we have, say, 3 variables, then gradient f at x naught, y naught, z naught gives us the direction of the maximum increase in the function. What does minus the gradient give us? If the gradient gives us the biggest increase, what do we think might happen with the minus the gradient? Yeah, I think I heard a mumbling of biggest decrease, and that's what it would be. Gives us the biggest decrease in the function. Okay, the opposite direction. Okay, now, so that's one significance of the gradient. We've already talked about that several times. But now we have this other thing. But if we have a level surface, then we just found out, then the gradient of f at some point is perpendicular to the surface. Okay. And question, is this a contradiction in some way? Okay. Well, let me stop the suspense here. On a level surface, if we're moving along a level surface, the value of the function doesn't change at all, because that's what a level surface is, where there's no change in the actual value of the function. So if the gradient gives us the biggest change in the function, intuitively it would make sense that that would have to be kind of far away from the direction of the surface as possible, which is perpendicular to the surface. Okay? So I'm just going to say this. There is no contradiction, and as we move, so I'm just going to put down what I just wrote, what I just said. As we move anywhere on the surface, fxy, fxyz equal to k, the values don't change. So it seems, shall we say, reasonable that the direction of maximum change or maximum increase is perpendicular to the surface. Okay, all right. I think I can get this in. This isn't much. Let's just, the very last thing I want to look at is just briefly when we have functions of two variables. Now, with functions of three variables, if we set that equal to a constant, we get a level surface, right? F, X, Y, Z equal to K, that's a level surface. Okay. But for two variables, F of X, Y equal to K, that gives us a level curve, right? That's like those contour curves that I had shown examples of. Now, here, the gradient also gives us the direction of maximum increase. That doesn't change. And this, with two variables, instead of the gradient being perpendicular to the tangent plane, it's perpendicular to the tangent line. And with two variables, the gradient is perpendicular to the tangent line. So let's just here look at this one little picture I've got here. Actually, let me just put the thing up here Basically what I have here is a XY plane. We have a function of two variables. So right along this contour curve right here, the function of two variables is equal to a constant. All right, so we have a contour surface. And let's look at this point right here on the curve. Instead of on the surface, now we're just looking on a curve. And the gradient is going to be, and here's our tangent line to the curve, just touching the curve. The gradient now will be perpendicular to the tangent line, all right? And I just got a couple of drawings here that I'll throw out here, and that'll be it for today. But let's just look at these. Here is one diagram that where we have the level curves of the function x squared minus y squared. And so all of these are contour curves at different values, 0, 3, 6, 9, all right? These arrows here are the gradients. So we see, first of all, that the gradients are perpendicular to the tangent lines of the curves. And the gradients also point in the direction of where the curve is increasing. So these gradients have different directions. This means it's getting bigger in this direction. Actually, this way, this means it's getting bigger up here going in this direction. And again, they are perpendicular to the level curve. And then last thing is this. It makes sense if you're say climbing a mountain or climbing a hill, what would be the hardest way to climb it? Straight up, exactly. And that's what this is showing right here. Here we have a topographic map, so to speak, different elevations. And so if you say, I want to get up this thing the fastest way possible, but also the hardest way possible, I'm going to keep going at 90-degree angles to the level curves of this hill and keep going, which is along the gradient directions. So every place, I'm choosing the absolute hardest place to climb, but I'll also cover the less distance getting up the hill. All right. And that's it. Thanks for staying over a couple minutes.